Okay. So I realized that part of some of homework problems involve one-sided limit, which I haven't I'm not going to get to until today. So sorry about that confusion. Sometimes the homework doesn't quite line up with what I've gone over yet. So hopefully that doesn't happen too often. Now, some of you guys were showing me your homework directly on your sheet, which is fine. But as you get to problems that require more work, I do want you guys to use a separate sheet so you're not, trying to fit everything on your exercise pages. And then also, I just want to again make sure that on page 18 in your packet has all the AP multiple choice problems listed out. So if you want to do your work in your notes packet for the AP problems, you can do that. I guess so I think that may be a better place for it than with the limited space that you have directly on your exercise pages. Okay, so page 6. Okay, so a one-sided limit is not a true limit. It only tells us about the approach from one side or the other. So yesterday, when I had us draw arrows towards the destination, each of the arrows is a one-sided limit. Okay, so one-sided limit is the y value that a function approaches as you approach a given x value from either the left or the right side. So the limit, so this example here, the limit of f as x approaches 3 from the left side of 1. So if I pick an arrow, if I pick a point to the left of 3, and then draw an arrow towards my destination, if I just want to look at the behavior of just that arrow is headed towards a y value of what? -1. So this is the way that you would write it. X approaches 3. That minus sign means I'm approaching 3 from the left side of 3. So I'm starting at 3, 2.1, 2.2, 2.3, and then headed towards 3. Okay, however, the limit as x approaches 3 from the right side of 3. So I'm going to pick a point on the other side of 3, make it head towards my target. But it's the notation here is 3 with a plus sign here because I'm starting to the right of 3 and headed towards 3. And that is headed towards a y value of what? 2. So a one-sided limit can exist, but really we use the language of one-sided limit to indicate whether the true limit exists. Right. So are these numbers in agreement? They're not. So that indicates that we can now use a formal language to identify whether a true limit exists rather than saying, oh, the arrows don't match up. We can use a more formal language to indicate that. So if the two sides are different, so we can say because the limit as x approaches 3 from the left side of 3. Now make sure that we can't just say this. I know we don't say it involving the f of x, but we got to make sure you always indicate what expression you're referring to. Okay. It is not equal to limit as x approaches 3 from the right side of 3 of f of x. Okay. And because these are not in agreement, the arrows, in other words, the arrows are not headed towards the same destination, we say that the limit does not exist. If you want to use abbreviation DNE rather than writing out does not exist, that's perfectly fine. Now, again, make sure you watch your notation. A lot of times in the past, I would see students write things like this, because that's the way that we say it. Limit as x approaches 3 from the left does not equal the limit as x approaches 3 from the right. But this is an incomplete notation because you have to identify what function you're referring to. So make sure you have either an expression or something that you're referencing. Okay. Don't just leave it blank like this, even though that's the way that we say it. Okay, so try example 2. See how far you can get by looking at the graph. And we'll compare our answers. Okay. Hey, go ahead and check your answers. Any questions? Okay, so I think it's relatively easy to look at a graph and identify certain characteristics. It's a little bit more challenging to be given a certain set of characteristics and try to fill out a graph that shares those characteristics. Okay. Any questions with example 2? Everybody good? All right, so let me show us how that could look. Just understand that if we're sketching a graph, everyone may have something a little different, and it could be fine, but I do want to kind of point out some things to keep in mind as you are building your graph. I like to start with the easiest information. So anything that's order pair has nothing to do with graphs or behavior around it. So I like to just go ahead and just knock those out. So 3, -1, that's an order pair. I'm going to go ahead and so hits here says sketch a graph of a function g that satisfies all of the following conditions. So g of 3 is -1. Okay, I'll go ahead and Check that one off. Next up, let's look at part B here. Limit as x approaches 3 is equal to 4. Now, again, something to keep in mind is that whenever you have just a limit statement, sometimes you don't know what's going to happen at that point for future that may show up in future characteristics. So I like to always, I know where my target is. I know my target is at order pair 3, 4. But I like to always put a hole there and just have my graph headed towards that hole. And if it ends up being that hole is getting filled in, I can always fill it in later, rather than having the graph go through that order pair and then having to erase and put a hole there when you realize that the point is defined elsewhere. So whenever I see a limit, I always just go ahead and identify that location as my target. And I don't want to overlap with other things that may conflict with it. So I just want to kind of have branches that slightly move out, and then I can finish the graph later once I see everything a little more clearly. So right now, that's just an indication for me that I know that my limit exists, but I don't know where my branch is going to fall yet. So I don't want to go too far. I may kind of, it allows me to have it allows me to not have to erase too much, especially if I can just fill that out later. Okay, so I'm going to leave that for now. I know I've fulfilled my condition for B, but I may want to make it a little prettier, a little cleaner once I know where I want those branches to go. Okay, so here, next up, limit as x approaches -2 from the right side of 2 is equal to 1. This is only a one-sided limit. I know my target is towards -2, 1, but only from the right side. So -2, 1, I'll put a hole there. I'm just going to put a branch that extends towards -2 from the right side of -2, but I don't know exactly where I want that branch to go yet. But at least I've started my I fulfill that behavior for that condition. Part D, they want us to show a graph that is increasing between -2 and 3. So I'm just going to go ahead and connect these points. Looks like I don't have anything that is preventing me from doing that. So I don't have, well, it says it's increasing. So it makes it obvious for me to just kind of make my graph rise between those 2 points, right, and make it connect. Okay, next up, I want my limit as x approaches -2 from the left side of 2 to be greater than the limit as x approaches -2 from the right side of 2. So here, my limit, my one-side limit is headed towards 1. So that means I want the one-side limit from the other side to be what? Greater than 1, right? So I just want, also, this indicates that I'm going to be creating something where the limit does not exist, right? Because if this is greater than, if they're not equal, that means the limit doesn't exist, but that's fine. We can just, I'll pick, again, this is where you have option to have something different than me, right? Because you can pick a point higher, much higher, or just a little bit higher. And I'm just going to have my graph go towards. Now, the important thing is that once your graph is done, you want to make sure that you don't have anything that is causing the function to not exist, right? We can't fail the vertical line test. So so every vertical line that you can imagine dropping, it should never hit more than 1 point on the graph. That's true, right? Okay. Yeah, that I think that is fine. You can either fill in this hole or fill in this hole or leave them both blank. Those are all valid. But if you fill in both holes, that's an issue. Okay. But here, there's no restriction from preventing us from filling in either of these holes. Okay, good. Next page. So we know how to read the graph and find a limit from a graph, but can we also find a limit using tables? So it's actually pretty easy because we just have to know how to interpret a table. So if we have a graph, it's easy to find the value as x approaches 3, right? So here I'm going to pick points on either side of 3. And are both arrows headed towards the same y value? Yes, they're both headed towards what? Y value of 4, right? Okay, so this is how a table would look. So here, again, we don't care what's happening at 3. We just want to see that the x value is headed towards 3, which it is, from both sides, right? So 2.9, 2.99, that's good. That's headed towards 3 from the left side, 3.1, 3.01. Now look at the y values here. The y value, this side is headed towards what? 4, and this side is also headed towards 4. So even if the point says a different y value, let's say order pair 3 is at 8, it doesn't matter, right? Because the limit is still going to exist because 3.99 and 4.01, that's a consistent movement towards the same y value. Right. So really, that's all we're looking for. If we're looking for a table, we should look to see, are the y values consistently moving towards the same value? If it is, it doesn't need to hit it. As long as the approach is the same, that's enough for us to say the limit exists. Okay, so here the function f is continuous and increasing. Table gives a value of f at selected values of x. Approximate the value of the limit as x approaches 2 of cosine of f of x. We don't have to do anything with the calculator. We just have to look at the table here. So here, my x value is clearly approaching 2, and my y value is approaching what? 5 from both sides, right? And again, we don't care what's happening at 2. Maybe at 2, it's undefined, or maybe at 2, it's at 9, or at 6, or -2. We care about the approach and not the order pair. They are completely different categories. Now this one, okay, sorry, my bad. The f of x is approaching 5, but notice that this is a little trickier here. It's asking for the cosine of f of x. So I'm going to insert f of x 4.999 and 5.001 into the calculator and see if those y values are headed towards the same y value. So sorry, this is one step more than what I was telling you. Okay. You can use your calculator or just follow along with me. If I insert the y value 4.999 into my calculator, cosine of 4.999 is 0.2827. Okay, that's a y value. If I insert 5.001 into the calculator into cosine, I get 0.2846. And if you look, these y values are still consistently moving towards something that I can say, right? This is 0.2827, 0.284. That is both on either side of 0.283. So I can make a pretty good estimation that my limit of cosine of f of x is 0.283. Okay, let's talk about finding limits using algebraic methods. So the first thing, whenever you are approaching a real number, no matter what you're working with, don't skip this first step, because the first step is important. Always do direct substitution. Okay, so even if you feel like you know what's going to go on, go ahead and insert your x value, because it's an important step because it helps you identify which category you're dealing with. Okay. Feels like an obvious step, but it's easy for us to jump the step, especially if we feel like we know where it's headed. Okay, so let's go ahead and just plug -1 in. So if I plug -1 in for x, I get -5. So what this tells us is that whenever you want to find a limit, if you can do direct substitution and get a real number in return, that's your limit. There's nothing more to do. Okay, and this indicates to you that it's a continuous function. Your order pair is going to be the same as your limit, so you're not going to do anything different. Only if we get something undefined or something a little strange, then we have to step back and do some more work to find the limit, especially if there's a hole. Okay, number 2, do I have a variable to plug in? No, so my limit is just always going to be 6, right? It's going to hold that y value all the way through. Okay, so number 3, again, we're not going to do anything different. Our first step will always remain the same if we are approaching a real number. Okay, if we're approaching infinity or negative infinity, we have a different set of steps. But if it's a real number, we always plug in. So let me show you what happens when things don't work out, and for us to be able to recognize that we have to do more than just direct substitution. So let's insert 0 in for x. What do we get? 1. Initially, what do we get? 0 over 0. So I want us to do something here. I don't want us to use an equal sign. I want you to do arrow 0 over 0. Right. Now, this is just something that College Board is picky with. College Board, they don't like to see equals 0 over 0. It's just something that they don't like. So they may take off points if they see an equal sign. Typically, I think they're pretty forgiving when students do certain things, but for some reason, this is something that they don't like. So this indicates if you see 0 over 0, it's indeterminate form. And visually, this tells you that there is a hole in the graph. Now, when you have a hole in the graph, obviously the point doesn't exist, but your limit does exist. We just haven't found it yet. So we never want to stop a problem here and say, oh, the limit doesn't exist. The limit does exist. This just tells us we have to do more work to get to our limit. Okay, so whenever you see a 0 over 0, that means there's a common factor that we can identify and we can remove. Okay, so let's see if we can find that common factor. What common factor do we have in the numerator? X. So a factor in x out. Okay, so I want us to understand that these two x's, this is what's causing this 0 over 0 to occur. Okay, so if I remove the hole, I can figure out where the true limit is. So once I remove the hole, I'm going to do direct substitution again, and this will lead me to the location of the hole, which will lead me to my true limit. So if I do direct substitution in for x, what do I get? -5. So that is your limit. So if you were to look at the graph would have a hole at a y value of -5, and that is how we can read and find a limit without having to rely on the graph. But we never want to just go ahead and start factoring and canceling out without first confirming that you're getting a 0 over 0. Okay, College Board is also looking for that as well. They want to see, if it's free response, they want to see that you're identifying it as indeterminate form before you look for the true limit. Okay, so
if it's on the same like plane, would you do the equal sign with the arrow? Or like...
Yeah, so I would say if you can use arrows all the way through. Okay, so here is the issue that College Board they don't like. Whenever they see an equal sign, they're going to ask their graders to look at both sides of the equal sign. They're going to ask, are they equivalent? If they are equivalent, then that's fine. The equal sign can stay. But if they're not equivalent, then there's an issue. Okay, the way that we use equal sign is we use equal sign a lot of times to indicate, okay, this is my next step, right? We really don't mean equal sign, but that's the way that College Board interprets it. So the safest thing to do on free response is just use arrows all the way through, just to indicate to the grader, hey, I'm just telling you what my next step is, but I'm not going to commit to these two things being equal. Once you commit to those two things being equal, then the grader has to look at both sides individually and actually see if they're equal, right? So it's just something that
you're gonna get penalized for using it, but you're not if you don't.
Exactly right. So if you just do arrows, that's a safe way for you to avoid getting penalized. So yeah.
Can you do upper tones?
Hmm?
Can you do upper tones?
Yes, but we will do we'll do L'Hopital's rule once we learn derivatives. But right now we're just dealing with this factoring. But yes, when we get to past this unit, we're going to have a potentially more efficient way to get to our limit using L'Hopital's rule. But right now we haven't learned derivatives yet, so we're going to rely on these methods first. Okay, so number 4, let's go ahead and try this one. Okay, so first thing, insert -7, do direct substitution. What do we get? 0/0. Okay, so that gives you the green light to factor and cancel out, because you know that you can't just say that the limit doesn't exist, right? We know that's not true. Okay. Trinomial factoring multiplies to be -7. So I have the middle terms here, 14x minus 1x is 13x. So there's my culprit, x plus 7. This is what's causing that 0/0. Let's remove it. Reevaluate. Sorry, approaching -7, not -2, my bad. So there's my limit. Okay, so the recap. If I do direct substitution and get a real number, I stop. That's my limit. Nothing more to do. If I do direct substitution, if I get 0/0, that tells me there's a hole, but keep going. There is an answer that's waiting for us. We just haven't found it yet. Okay, here's the third scenario here. Let's do direct substitution and see what happens for number 5. So if I do direct substitution, -6 in for x, numerator, what do I get? Okay, 15. But denominator, I get 0. So I want us to understand something. This 15/0 is different than 0/0. And that 15/0, it's indicating to us that the limit does not exist, because this indicates that there is a vertical asymptote happening here. So if you know that, if you can visualize it as a vertical asymptote, you know that the limit doesn't exist, because the graph is not going to approach the same real number y value from both sides of the target. Let me highlight a few things about zero. Okay, I'll just put a side note here. If I had 0/7, that's the same thing as what? That's 0. Okay, that's a real number. Okay, that we can leave alone and not do anything with it. Okay, but if I get 0/0, that's indeterminate form. You know, there's a hole in the graph. The limit does exist, but there's a hole. But if I get 9/0, that means there's a vertical asymptote and my limit does not exist. All right, so I want to make sure that we are clear about the different variations of zero. Depending on where the zero is, we have to interpret it appropriately. Okay, so now I want to talk about problems that have very specific methods other than factoring that allows us to reduce and get down to a limit when there's a hole in the graph. So whenever there's a radical in the numerator or denominator, sometimes we go through this method called rationalizing to allow us to arrive at the limit algebraically. So, but first things first, right? We have to make sure that we understand what category we're working with. So let's do direct substitution. If I insert 5 in for x, what do I get? Numerator, I get 0. Denominator, I get 0. Okay, I know there's a hole. I know that there is something that's preventing me from getting a real number out of it, but I know the limit does exist. Okay, so here's the strategy here. We're going to multiply the numerator and denominator by the conjugate of the numerator. Okay, so we're trying to find a way to get that radical to look something a little different that's easier to work with. So the conjugate is the same as my numerator expression. I'm just going to slightly change that sign to a different sign, and that will allow for the foiling process to work out cleanly. Okay, so if I multiply by the conjugate, remember, anything I do to the numerator, I can also do to the denominator and still maintain balance. Okay. We don't change what's inside the radical. We only change the sign between the terms. Okay, -3 and a +3. Now we're going to FOIL the numerator out. The numerator will FOIL out hopefully to a form that will match this x minus 5. This is the culprit here. X minus 5, that's causing a 0 in the denominator. There's an x minus 5 hiding in the numerator that we don't see. But once we identify it, we're going to cancel them out. Now here's the thing. FOIL your numerator, but leave the denominator alone. Okay. The reason why you want to leave the denominator alone is because this x minus 5 is ready for you to cancel out. Okay. So if you expand this out, you're going to lose that x minus 5, and you have to factor it out again. So it's not. So just know that the numerator is what you're working with. The denominator is ready for you to cancel out. Okay, so I'm going to FOIL this out. Root x plus 4 times root x plus 4 is equal to just what? X plus 4. The nice thing about these minus and plus is that the middle terms will drop out. So -3 root x plus 4 plus 3 root x plus 4 will just nicely go away. That will 0 out. We should have to worry about these last two terms here. -3 times 3 is -9. Leave the denominator in factored form. Now, what do you notice about the numerator here? Becomes x minus 5, right? So once that becomes x minus 5, that's a perfect match with the denominator. There's my culprit. There's the hole that I removed. Now, everything in the numerator goes away. There's still a what left over? A 1. Okay, so now the whole is gone. We should be able to reevaluate and get down to a real number. So replace the remaining x with 5. Root 5 plus 4 is root 9. Root 9 is 3. 3 plus 3 is 6. Don't forget, it's not just 6, it's 1 over 6, right? There's a 1 in the numerator. Any questions with those steps? Okay. Try number 2. Follow the steps that you did with number 1. Don't jump into your steps without first confirming that there's an issue. So do direct substitution first. Confirm that there's an issue before you commit to the conjugate method. So here's a little bit different. The radical is in the denominator, so you're going to try to clean up that denominator, but you're going to leave the numerator alone because you know that x minus 10 is what eventually you want to pair up and go away. Okay, we're getting 0 over 0. There's a hole. Let's go ahead and find that hole. There's the radical in the denominator, so multiply by the denominator's conjugate. And we're hoping that the denominator will clean up in a way that will match that x minus 10 in the numerator. So if I FOIL out that denominator, I get 9 minus parentheses x minus 1. Got to distribute that negative through, right? So 9 minus x plus 1 gives me 10 minus x. Now, is this a perfect match? Close, but not quite. But I can make them the same if I do what? Yeah, if I factor -1 either from numerator or denominator. So I can cancel these out. Just make sure that there's a -1 that's going to leave. That's going to be left over. So I'm going to cancel them out once I factor a -1. And once I have that -1 in place, I'm going to reevaluate, do direct substitution, and then that should lead me to a real number. Okay, there's one more category algebraically of finding limit when there's a hole, and that is with complex fractions. Okay, so let's look at number 3. Okay, so number 3, limit as x approaches 0. You see how there's that complex fraction in the denominator, but let's not jump to conclusions. Let's go ahead and do direct substitution. So 0 in for x. What do I get? 0 over 0. I get -1/4 in the denominator plus 1/4, which is 0. So we know that the limit does exist. We just need to do more work to get to that true limit. So here's the strategy that we're going to do here. We're going to try to focus our attention on just this portion. Okay, my goal is trying to get that to merge into one fraction. I'm going to have to do common denominators here. So I'm going to step to the side here and just focus my attention on trying to get this cleaned up. So what's my common denominator that I can share between these two fractions? 4 times x. Yeah, 4 times x minus 4. So I'm going to go ahead and write this out twice. That's my goal there. Now I'm going to be trying to balance each fraction. So this x minus 4 is missing a 4. I want to go from here to here, but I need to multiply the numerator by 4 in order for me to get that fraction to balance. This 4 is missing a denominator of, or missing a term of x minus 4. So I need to multiply the numerator by x minus 4 to balance that out. Now that I have common denominators, I can merge them into the same fraction. So 4 plus x minus 4, 4 minus 4 is 0. I get x over 4 times x minus 4. So this is now my cleaned up version of my messy denominator. So now I'm going to replace this mess with something that's a little bit cleaner to work with. So I'm going to rewrite the entire problem here. Okay, it doesn't look like we made much progress, right? Because we're still dealing with a complex fraction. But the nice thing here, now I have a numerator divided by a full, just one term denominator, one fraction denominator. Okay, so now I'm going to try to merge these together. I know that dividing by a fraction is the same thing as multiplying by the what? Reciprocal. So I'm going to bring that up. So the x is going to stay. I'm just going to flip this denominator. Instead of x over 4 times x minus 4, I'm going to make it 4 times x minus 4 over x. Now, what do you see here? Yeah, so this is what we know that's the culprit, right? This x is giving us that 0. So we're looking for another x, and we did find it. So once that goes away, we're in the clear. We reevaluate our limit. We should be get to a real number. So if I insert 0 in for x, 0 minus 4 is -4. 4 times -4 is -16. That's my real number answer. Okay, so that should help you get through your homework. I would want us to do number 4, but I feel like we're running out of time. So your homework tonight's look in your calendar, and hopefully everything is covered. Okay, come up and get your phones. Are you guys able to find my solutions on my website and be able to check answers? Okay, good. I'll make sure that everything that you do, I want to make sure you have the resource to check your answers. All right, come and get your phones. Okay.
I just copied the note.